Hello guys, nice to see you. So today we continue to consider uh, electromagnetic waves. In particular, we will quantitatively describe the behavior of plane, so-called plane electromagnetic wave. We will derive the speed of projection or spreading electromagnetic wave in free space, in vacuum, that will be equal to speed of light, and which was experimentally measured already previously before this theory was developed. And that will be a very clear provement that light is a certain form of electromagnetic wave. So then we will consider certain features of equations which describe time and position dependence of electromagnetic waves for vectors of electric and magnetic fields. So this is the plan for today's lecture. It's quite a lot of derivation. That's why let's dive into this. I change the camera, and let us consider a wave which is moving, like, spreads along axis x. We have system with three axes. We have x, z, and y. So we consider that in this case, electric field vector is oriented along axis y, magnetic field vector along axis z, and its direction of motion, like the velocity vector, call it c, is along axis x. So in this case, we deal with electromagnetic wave, which is linearly polarized. So we have certain direction for the planes where electric field vector and magnetic field vector are changing. Also, we should consider that such waves can be generated at any point of this zy plane, not only in the origin of the system of coordinate. And also necessary to mention that electric field vector and magnetic field vector, they are functions of coordinate x and time. The same stands for magnetic field vector. So they do not depend on coordinate y or z. So the ray, by definition, is the line along which the wave is spreading. So if, for instance, we consider generation of electromagnetic waves in many points of simultaneously in the same phase along plane which is defined by y and z axis, then these rays will be just straight lines which are parallel to axis x. They will go along the spreading of electromagnetic waves, and such combination of waves generated at the same plane in the same phase. They are called plane wave, the resultant wave which is formed, and also the surface which connects all points with equal phase of electromagnetic waves will be called the wave front. So a wave front is a geometrical system of points where wave is possesses the same phase, which is this definition was given previously in our course of Physics 1 last semester when we considered mechanical waves. So this definition is also true for electromagnetic waves. So now, in order to proceed further, we start with the Faraday's law, which is linear integral over closed path of electric field vector is equal to minus the rate of change of magnetic field flux over time. So with this equation, we need to, in order to apply this Faraday's law, we need to first calculate the left side of the equation, this linear integral along the closed path. So we need to define the path, the direction along which we will integrate it, and perform this integration. So for this purpose, let us consider one more figure. So here will be also 3 axes, z, x, y. So let us select some rectangular so here are vectors of the electric field. This vector is E as a function of x. Here is E as a function of x plus dx. So it's in certain instant of time. So time is a given number which doesn't change. So we just consider changes of electric field vector as a function of coordinate. And here we have this width of the rectangular dl, and this is the length of the rectangular L. So we will integrate this so here this rectangular the sides of rectangular, they define the path, the closed path over which we are going to integrate. It will be done in the counter clockwise direction, like this. And we already can say that along top and bottom sides of the rectangular, this linear integral of electric field vector will be equal to 0 because electric field vector will be perpendicular to the path, like this element of the path. And that will result in linear integral equal to 0. So we have two components to this linear integral, the left over the left side of this rectangular and over the right side of the rectangular. Also, it is necessary to show here magnetic field vector, assuming that dx, oh sorry, it's not dl, it's dx here, the width of the rectangular. The dx is small, it's much smaller than the wavelengths of the electromagnetic wave. This magnetic field vector can be considered as constant and just perpendicular to the surface, like dashed surface, defined by the closed path of our rectangular. So let us first define what will be electric field, like value, magnitude of electric field vector in at the right side of the rectangular. So we can write that. Delete this. We don't need this anymore. So the electric field vector Ex plus dx will be equal to Ex, means magnitude of electric field vector at the left side of the rectangular, plus dE over dx, derivative at t time equal constant, times dx. So assuming that we have, we agreed at the beginning that our electric field vector and magnetic field vector are functions of two variables. So when we fix one and take derivative over the other, it means partial derivative. So we can rewrite this expression. It will be Ex plus sorry, now we have partial derivative. It will be this d E over dx times dx. Okay. So now we have expression for the magnitude of electric field vector at the right side of the rectangular, and we can calculate the linear integral along this rectangular. So this linear integral is equal to E vector times ds, like over dx. So it will be, since we integrate in the counterclockwise direction, so this will be Ex plus dx times L minus, because they are parallel, this side of the right and left sides of the rectangular are parallel to the electric field vectors. So we just have products of the magnitude of the vector to the length of this side, minus Ex times L. So, and this is going to be approximately equal with certain accuracy, level of accuracy, to L times dEx over dx times dx. Okay, so this is the left side of the Faraday's equation. Now we need to find the right side, and we can see, assuming that dx is very small, as we mentioned above, and b vector of magnetic field vector is its magnitude is constant within this interval of dx, we can write that magnetic field flux is equal to the product of b, L, and dx. So it's just product of magnetic field vector and area of this rectangular. At the same time, we need to take derivative. So it will be db over dt is equal to L times dx will be db over dt at x constant, which is also partial derivative. So it will be L times dx db over dt. So we have the right side of the Faraday's equation. Just we will need to put this minus here later when we put them together, and let us write the result of applying Faraday's law for our system. Let's go to another slide. So in this case, we can write that we have L times dE over dx times dx is equal to minus, what did we get there? It's L dx dB over dt. L dx dB over dt. So automatically from this equation, we can get the first equation which we want to use for the derivation of the speed of spreading of electromagnetic waves, that dE over dx is equal to minus dB over dt. And this equation we will mark with 1 star. So it's like 1 star equation. Now let us go further. And in order to get the second equation which we need to consider Ampere's Maxwell law, which is force Maxwell's equation. So let us write it down so we know with what we are dealing. It will be integral over closed path of vector magnetic field vector equals, so we do this for the free space, we don't have any conduction current there, that's why we have epsilon 0, just only displacement current contribution, epsilon 0 times mu naught d Fe, rate of changing electric field flux with time. So we need to calculate both sides of this force Maxwell's equation. For that, for the left side, we also need a figure with 3 axes. So this will be something like this. X, Z, and Y. Now we will consider ZX plane. Here we also choose a rectangular path. So we have here dx, the width of the rectangular. Then we have the length of the rectangular L. Here we have magnetic field vector Bx, and here is another one, which is Bx plus dx. So again, assuming that dx is much smaller than the wavelength of the electromagnetic wave, we can assume constant electric field vector E. And in the same manner, we define value of magnetic field vector at x plus dx in comparison to B, like magnetic field vector at the position x, as we did for electric field vector, and integrate in the counterclockwise direction while looking from the top on this plane zx. So this will be like this. So with such orientation, this linear integral along the closed path defined by the our rectangular will be equal. So here we will have Bx times L minus Bx plus dx times L. And this is roughly equal to minus L dB over dt, dx times dx. Okay, so the left side is ready. Now we need to calculate the right side. So the electric field flux through this surface of the defined by the rectangular will, assuming that electric field is constant because dx is very small, we get just product of constant electric field vector times L times dx, area of this rectangular. And we need a derivative over time here. So this partial derivative of of the electric field flux dFE over dt will be equal to L times dx times dE over dt. So now we have left and right side of the Ampere-Maxwell equation, so we can put them together, and that will result in such equation, the second equation we need. That will be partial derivative of magnetic field vector over x position will be equal to minus mu naught times epsilon naught d e over dt. So this is our second equation. We will mark it as double star equation. Let us write down these two equations on the next slide, because we will use them for further derivation. Okay, so d will be d e over dx is equal to minus db over dt. This is equation star, and let us write next to it the second equation which we got, db over dx is equal to minus mu naught epsilon naught dE over dt, and this is double star equation. Okay. Now what we are doing, so we need to take the derivative of equation star with respect to x, and combine that result with the derivative of double star with respect of t. So let us do this. So first we take derivative of equation star with respect to x. That will be d squared e dx squared is equal to minus d over dx db over dt. Now we take derivative of the equation double star with respect to t. So this is d over dt db over dx equal to minus maybe we can put minus later in the parentheses. So this is d over dt of minus mu naught epsilon naught dE over dt. Okay, so what do we get? Here we see that we have the same terms in the right side of first equation and the left side of the second equation, which just we have dx and dt, and here dt dx. So these are two partial derivatives of magnetic field vector, and it doesn't matter which of these partial derivatives we take first. The result will be the same. So that's why we can claim that these two terms are equal with the factor of the sign. So we can write that d squared e over dx squared is equal to minus d over dt of minus mu naught epsilon naught dE over dt. And obviously these two minuses cancel each other. So eventually we get mu naught epsilon naught dE square over dt square. So this is first equation which we get for electric field. The same procedure we can do for magnetic field vector. And for that purpose, we need combine the derivative of double prime equation with respect to x with the derivative of the prime equation with respect of t. So if we do this, so let us write this down here. So we'll have d squared b over dx squared equal to d over dx minus mu naught epsilon naught dE over dt. And second, we need to take derivative of the one-star equation with respect to t. So that will be d over dt dE over dx will be equal to minus d squared b over dt squared. So again, we have the same components here, like two partial derivatives of electric field vector here and here. So when we so we can write that these two terms of the left term of the first equation and the right term of the second equation, they are equal with respect to certain sign. And eventually we get d squared b over dx squared is equal to minus mu naught epsilon naught minus d squared b over dt squared. So with respect not only to sign, but also to the product of these two constants, because here we have these constants and here we don't have them. So we need to take this into account. So eventually this will be equal to mu naught epsilon naught d squared b over dt squared. So we got the same equation as here, this one. First one for electric field vector, another for magnetic field vector. So let us write them down now and the next slide, because these equations are very important. So we can write that d square E over dx squared is equal to mu naught times epsilon naught d E squared dt squared. And another equation for magnetic field vector is d squared b over dx squared is equal to mu naught epsilon naught d squared b over dt squared. Okay, so we have these two equations, and if you recall our previous course, Physics 1, we considered this similar type of equations for for mechanical oscillations. So this is so-called general wave equation. So general form for this will be d squared y dx squared is equal to 1 over v squared is the speed of spreading the wave times d squared y over dt squared. So this is general form of wave equation. And as I mentioned, this v is the speed of wave, and y is the wave function, which is a function of x and t. So in our case, we have wave function is our electric and magnetic field, and according to the same structure of equations which we got for electric and magnetic field as a function of coordinate and time, we can write in analogy to this speed of spreading of the wave, that speed of electromagnetic wave, c, is equal to 1 divided by square root of the product of these two constants. It will be mu naught times epsilon naught. If we substitute the values for these constants, we will get the speed of light, 2.99792 times 10 to 8 meters per second. And this is this theoretically calculated speed of electromagnetic wave is exactly equal to speed of light, which was previously measured before this theory was developed, which is a very bright provement of the nature of light, that it is just electromagnetic wave. So this is a very bright example of complementary of contributions of theoretical and experimental physics. So since these equations for electric field and magnetic field vectors follow obey this general wave equation, we can write for the wave functions the following dependence on x and t in some explicit form. Will be E maximum times, oops, it's not, cosinus kx minus omega t. And for magnetic field vector, B maximum cosinus kx minus omega t. So this is the forms of this wave function functions which satisfy this general wave differential equation. And so we are also familiar with these equations. They were considered for mechanical waves also in the previous course. So here k is equal to 2 pi divided by lambda, and this k is the wave number, and lambda is a wavelength. Omega is the angular frequency, 2 pi times f, where f is the wave frequency. So what is important to know that the ratio of angular frequency to wave number, this is equal to 2 pi f divided by 2 pi lambda, and this is, oh sorry, here is divided, 2 pi divided by lambda. This is equal to lambda times f, and this is equal to c, speed of electromagnetic wave. In its turn, lambda wavelength is defined as the ratio of speed of electromagnetic wave. So in this case, we consider free space, vacuum, divided by the frequency of the wave. So these main parameters of wave functions which describe time and x and time dependence of electric and magnetic field vectors are defined. So let us proceed further to the next slide and consider derivatives of these functions. We will take partial derivative of electric field with respect to x and magnetic field with respect to t. So let us write d e over dt. Oh, sorry, not dt, dx. dt will be for magnetic field. Is equal to minus k times E maximum times sinus kx minus omega t. And partial derivative of magnetic field with respect to time will be equal to omega times B maximum times sinus kx minus omega t. So taking into account the prime equation, which we derived earlier, let us write it down here. It will be d e over dx is equal to minus d b over dt, which actually tells that there is a relationship between changing electric field vector over position along the propaggation of the spreading of the electromagnetic wave with the change of magnetic field vector with time. So this is this equation prime, we called it, like a star. Taking this into account and the results which we got here, we can write that the ratio of E, like maybe first, let's write that K times E maximum is equal to omega times B maximum, because these left sides are equal with the factor of this sign minus. Sinus is the same here as here, so this coefficients in front of sinus, they should be equal to each other. So the ratio E maximum over B maximum is equal to omega divided by K, and that is equal to speed of wave, speed of light actually, as a constant. And since this is true for the ratio of the maximum values of electric and magnetic fields, this ratio is also true for any for any time instant for electric and magnetic field, for magnitudes, ratio of magnitudes of electric and magnetic field at any instant of time will be equal to E maximum to B maximum and equal to speed of light. So this is very important conclusion, that at any instant of time, the ratio of the magnitude of the electric field to the magnitude of the magnetic field vector in an electromagnetic wave is equal to speed of light. So that is the feature of electromagnetic wave. So we derived today the expression for the speed of electromagnetic wave, which gives us the number equal to the previously experimentally measured speed of light, showing that light is electromagnetic wave, nothing else. And also we have shown that this ratio at any instant of the magnitude of electric field vector and magnetic field vector is equal to speed of light. So our next topic, which we will consider on Friday, will be the energy carried by electromagnetic wave, and also the momentum, which is carried by electromagnetic wave. So and also radiation pressure of light. Apparently, it does exert some pressure on the surface. So we will derive these equations which describe energy and momentum of electromagnetic waves carried off by electromagnetic waves, and consider different parts of broad spectrum of possible electromagnetic waves, also considering some ranges where these different wavelengths of electromagnetic waves have found their applications. Okay, thank you very much for attention, and see you on Friday. Take care and have a good evening. Bye-bye.